Hello! In this video, we're going to justify the observation that the ratio of the masses of the constituent elements in any pure sample of that compound is always identical on the basis of the atomic molecular theory. So basically, you're going to do two things here. One, you're going to explain the law of definite proportions and apply the law of definite proportions to samples of compounds. And two, you're going to perform mathematical calculations involving weighted averages. First, some fundamentals from year one. All matter, you, me, everything that has a mass and takes up space is composed of atoms. Two, there are a limited number of different types of atoms. Each different type of atom is an atom of a different element. The elements are organized on one of the best documents ever created, and that's the periodic table. As we take a look at these two samples that are currently on your screen, both of these would be classified as elements. As we take a look at the sample on your left, I hope that's your left, this sample is composed of just one type of atom, this green atom. Again, as we look at the sample on the right, although there are two atoms bonded together, they're both the same atom. This is known as a diatomic element. Regardless, both of these samples would be classified as elements because they're made up of just one type of atom. Whoa, clear. An important thing to remember as you use your periodic table. Don't forget that those masses displayed on the periodic table represent the average atomic mass, and that a large number of atoms of any single element is always going to have that same average mass. And that average mass is determined by looking at the mass of each of the individual isotopes and the percent abundances, and can be solved for by using the following formula. Boom. So as you struggle to wrap your mind around the idea of average atomic mass and how that works, let's imagine we had an element made upium. And let's pretend we had 100 atoms of this made upium. And this element consists of two different isotopes in nature. Those would be made upium 10 and made upium 11. Well, if we look at those 100 atoms of made upium, or any sample of 100 atoms of made upium, that 99 of those 100 made upium atoms are going to be of this isotope made upium 10. Whereas just one of the 100 atoms consists of made upium 11. So if we were to do just a straight average and take 10 plus 11 divided by 2, we would get an average mass of 10.5. But if the majority of the atoms are made upium 10, and only one of those atoms out of every 100 is made upium 11, it doesn't really make sense to have an average mass of 10.5. In fact, that's the rationale behind weighted averages, giving more weight to the things that there are more of. God, I'm such a genius. Next page! Once you get two or more different types of atoms together, we start forming compounds. As we look at this representation, we've clearly got a compound. We've got two different elements chemically bonded together to form the compound. The red one and the white one. And the fifth really important part, and the fifth fundamental concept to walk away with from today is that a pure compound is always going to have the same whole number ratio of different atoms. For example, water is always H2O, and the ratio of the masses of the elements is always the same in any given compound. It doesn't matter if you have a teaspoonful of water or if you got a swimming pool full of water. The ratio is always going to be 2 hydrogen to 1 oxygen. Consequently, then, if the whole number ratio of the atoms, and therefore the ratio of the masses, changes, then a new compound has been formed. For example, H2O2 is not water. It is hydrogen peroxide, a different compound with a different ratio of atoms and a different ratio of masses of hydrogen and oxygen atoms. All of this can be summed up in one of my favorite chemistry jokes about two chemists who walk into a bar. The second one, well,